All right, good morning, everyone. We're in the home stretch. So last week's going to be the last week of lectures, so we're trying to get through the core nugget of material on radiation. Right? So in the last lecture, we talked about primarily this idea of what a solid angle is. Right? It's sort of the analog to a regular old angle like you all grew up knowing and loving in geometry, right, to a three-dimensional space. So to quickly recap that, let's zoom in, change to black marker. Let's recap that, right, a solid angle is the surface area projected or of a unit radius sphere where it intersects a subtended angle of an object. And so what I mean by that is, the example was if we've got little Billy out here watching the solar eclipse. We've got the moon, we've got the sun. The idea is that these both subtend the same angle. In other words, they occupy the same visible region of space. And if you were to draw a sphere of radius 1 centimeter around this point here, 1 meter, then the surface area on that sphere where it intersects this cone would be what's known as the solid angle. But solid angle doesn't have units of surface area. Okay, this is the only thing I want to point out. So we call that omega in units of steradians. So omega is defined as the area of the silhouette of whatever it is you're looking at. Okay, so the projected area divided by the squared radius to that silhouette. Okay. So you can see here why if r is equal to 1, then it simply becomes a. So the solid angle is really important because, like I mentioned, it helps us sort of divide up this idea of physical space. And it's especially important for optics because optics and radiation and electromagnetism generally rely upon this idea of like line of sight. So the question is, the issue is, this is still sort of this should make some sense intuitively, but it still kind of it's a little mushy mathematically, right? How do we represent a solid angle in more familiar terms? We do so by using spherical coordinates. So if we consider our spherical coordinate system, right, it's usually defined by, if we have it in a three-dimensional space, it would be defined by, if we have some radius r, which is at what's known as some zenith angle theta, and then if we projected this down onto the horizontal plane here, this rotation about the vertical axis is what's known as the azimuth angle phi. So 3 variables, r, theta, phi. If we wanted to, we could use these 3 to represent sort of to kind of paint what the solid angle actually is. So if we were to project out not a cone, but sort of a rectangular pyramid. Okay, so if you make this a little piece of the surface area of a sphere. Imagine that we've got a sphere going around the origin here, and this is just a little patch of that surface, which we'll go ahead and call dA. We'll skip most of the most of the process of actually painting kind of how we do the projections and such here, but trust me in that we could go ahead and write this dA as r squared times sine theta d theta d phi. The reason being, essentially, that we could represent the width of this as r sine theta, and then anyway, yeah. So go ahead and check out section, I think 12.3 if you're not convinced of this, but for now it's not very intuitive, but similar to the way that the arc length of an item is r dr d theta, or an area in cylindrical coordinates is r dr d theta. We have r squared sine theta d theta d phi. So if we wanted to define the solid angle of this kind of rectangular pyramid, okay, this projection, this subtended angle of this little patch of surface area at the origin has some solid angle, right? It's taking up some visible portion, or some portion of the visible space as seen from that origin. And so we wanted to say that omega here is equal to dA over r squared. And this simply turns into r squared and theta d phi over r squared. Kill off the r squareds, and we have sine theta d phi. So this is how we're going to write. We're going to use this substitution a lot right here. And because we're talking about a very small solid angle here, right, the solid angle of a very small surface area, let's go ahead and put a d omega in front of it so that we recognize it's just a tiny little piece. So as is usually familiar when we put d's in front of things, the idea is we're going to be using this in an integral at some point. And so if we wanted to integrate over in a big region of space, for example, let's say this is exactly what we're going to be doing. If we wanted to integrate the amount of radiation going out to the entirety of visible space, okay, the idea is we would integrate over the collection of all solid angles from that point. But it's difficult to integrate over a solid angle. What are your limits of integration there? So instead, we are going to make this substitution, we're going to integrate in terms of spherical coordinates. So it just makes it more manageable mathematically. Okay, so we're going to move on from this purely geometric idea of what a solid angle is and start using it. So I want to there are a couple of definitions we're going to need to really crunch through today. Hopefully we start transitioning out of the definitions and into some actual practical stuff. So I want to define this thing that's called the spectral radiation intensity. Okay. Oops. And what the spectral radiation intensity is, in words, is the rate of energy radiation at a specific wavelength in a particular specific direction. Per unit projected area per unit wavelength and per unit solid angle. Okay, and so we define this as, it's known as this variable I, lambda, theta, phi, lambda. And so what this is doing is it's basically telling us, right, if we have something that's radiating energy out, or as we'll see in another case, right, being irradiated by energy coming in, the idea is this represents sort of the distribution of where that radiation is going or coming from, both in terms of space and in terms of wavelength. Okay, so for example, you take your laser pointer and you shine it at a particular spot in the ceiling. Okay, you as an entity, or kind of the wrapper around you, are radiating energy. Okay, but you have a particularly focused amount of energy being radiated in the direction of that laser pointer at the particular wavelengths that form that laser beam. And so the idea is that this captures the non-uniformity of the way that energy gets shed in different directions and at different frequencies of electromagnetism. So the issue is this is messy to work with, so we're going to work on trying to simplify this down into something that's more, of greater engineering utility. So I want to pay a little bit of attention to this idea of the projected area. Okay, this is going to become important as well. So let's imagine we've got some rectangular surface right here. We'll go ahead and say. Okay, so some rectangular surface here, and we're interested in figuring out how much radiation is being shed, perhaps in this direction. Okay, so this ray here is defined by a theta and a phi. And then let's say we're interested in figuring out how much radiation is being shed, not just in this direction, but it has to be shed across some solid angle in this direction. So if we put an object in its path, okay. So the question now becomes, how much radiation is being shed from this particular point, okay, from this little point on this surface in this direction across this small solid angle. And finally, so we could add that up. We could count up the total radiation that's leaving. But the way we normalize it is by projected area. And by projected area, I mean that if this object here became, the lens of a camera, or became an eye looking downward at this surface, what is the actual area that it would see? It's not going to be the square, differential area 1 that actually exists. What the eyeball located at this ray is going to see is a projection of that area. Oops. Okay, that has an area dAn, which is equal to dA1 times cosine of theta, where okay, right, so if, for example, theta was 0 degrees, I should mention theta here is, once again, this is the zenith angle measured from vertical plane. That if theta was 0 degrees, the idea is that we'd be the direction in which the radiation is being sent would see this entire area as projection. Whereas if theta were 90 degrees, then that cosine theta would be equal to 0, which means that the direction in which that radiation is being sent is able to see none of this surface area. So this just has to do with that perspective on a surface area. Okay, so with that definition out of the way, let's go ahead and define this guy right here, this spectral radiation intensity. So I theta, we'll start out with what's known as the emitted spectral radiation intensity. So this E here stands for emission. Okay, is written as dQe. That is that little bit of radiated energy that's heading out along through some solid angle at some direction at some wavelength, divided by dA1 cosine theta, so there's that projected angle, times d omega d lambda. So this will have units of watts, right, per unit projected surface area, per unit solid angle. So if you shrink down this solid angle, the idea is that there's going to be less total energy contained within that outgoing radiation, and per unit wavelength. So again, if we said if this is like a red laser beam, then it's going to be all that radiation is going to be tightly clustered around that one wavelength. And so what you do is you say, you take a very small little interval of those wavelengths, as you do in all differential calculus, and you say, here's how much energy is contained in this small little interval of wavelengths, and then you divide by the width of that interval. So it gives you the approximate sort of density of energy per wavelength. So from this, right, let's say we know this, right? What this is useful in doing is being able to calculate energy fluxes from this idea of spectral radiation intensity. So if we wanted to figure out what the flux of the emitted energy flux is of a small little surface area, then we could write this as, we'll say this is a function of wavelength and direction. So it'd be the spectral radiation intensity, which is a function of wavelength and direction, times the solid angle through which it's projected, times cosine theta. All right. So, well, let's go ahead and write we'll just reorganize times dA1 cosine theta. So here's the actual heat rate being emitted by a small area that's radiating energy, and that heat flux that's associated with that is simply going to be dQe divided by dA1. So that'll be I theta E, which is a function of theta, or lambda theta phi, times d omega times d lambda times cosine theta. So, right, heat rate, heat flux, same as we've been talking about here. The only thing to note here is that this heat flux, right, has to be heat rate per unit area. That area is not the projected area. So this is where things get a little bit confusing. So it helps to write this down. When you're dividing the total, like the amount of radiated energy by a surface area in order to get this double prime here, you need to make sure that it's actually the physical surface area of the emitting object, not the projected area. So this will, of course, have units of watts per meter squared. And this radiation intensity, okay, spectral radiation intensity will have units of watts per meter squared micron steradian. Okay. This is really not intuitive math. Okay, I recognize that. So we're going to say this is as complicated as it gets. But I want to highlight when this is useful. If you're given this function, okay, if someone has measured the spectral radiation intensity that's being emitted by an object, and you're given that as a function of lambda, right? The spectral content, the function is over different wavelengths, and across a range of different spherical coordinate angles, right? Then it's fairly trivial to actually integrate over some of those spherical coordinates and figure out how much energy is being radiated in a particular direction. So the takeaway kind of conclusion of this line here is that, right, emitted power is radiated away with an intensity that varies both with the wavelength and with the direction in which that radiation is occurring. If we wanted to relate this back to this idea of emissive power, or big E, there are two steps we can take. The first is to define what's known as the spectral emissivity. And this is simply 0 to 2 pi, integral from 0 to pi over 2 I lambda E lambda theta sine theta d theta d phi. Okay, and this is known as the spectral emissive power. So this is sort of what we were just talking about, how you can integrate over a region of space. Let's talk about what's going on here. These differentials right here, that sine theta, d phi, okay? Remember from our earlier little sketch of the spherical coordinate system that this is actually just the omega. So this is a little piece of a solid angle. Okay, so what we're talking about here is the amount of radiation in a given direction per unit solid angle, and we're multiplying it by a small, right, a small differential solid angle in a particular direction. And then these limits of integration simply represent, right, 0 to 2 pi, that's a full circle, okay, and 0 to pi over 2 means from horizontal to vertical. So what this is doing is it's integrating over an entire hemisphere. In other words, it's saying, right, let's say we've got an emitter right here that's casting out energy. What this is doing is it's integrating how much energy is being emitted over this entire hemisphere that is visible to that emitter on a surface. And so you'll sometimes see this referred to as the hemispherical spectral emissive power, but we're not going to drop that because it's sort of, we're not going to use that because it's sort of redundant. And then finally, if we wanted to know what the total emissive power is, right, this is the E we talked about in Chapter 1 and talked about again in the previous couple of lectures. E then is defined as the integral from 0 to infinity of lambda d lambda. So, right, if this is the amount of emissive power per unit wavelength, integrated over all wavelengths, and we get the total amount of emissive power. these two right here are going to be our bread and butter. The reason is, okay, as engineers, we need to understand that radiation occurs, right, preferentially in different directions. Like I said, the example of like shining a laser pointer or certain types of surfaces will tend to emit primarily in one direction. But as heat transfer people, we're usually interested not in, how much radiation is being cast off in some particular direction, but how much total radiated energy is being cast off, because that's how we add up do the bookkeeping for the total energy in and total energy out. That's going to allow us to do our energy balances. So what this is doing right here is this is saying over all space that is visible from a surface, here's how much energy is being emitted, sent out into the world as a function of wavelength. We're not going to be able to ignore the wavelength dependence, but we are essentially integrating through and pretending to ignore the directional dependence. And then if we happen to know the distribution of E as a function of wavelength, and we'll see in the next lecture how we actually get that, then we can go ahead and integrate through those wavelengths and figure out how much total power is being sent out. And then we have an energy flux. We have E. We can plug that into our energy balance, figure out how quickly something is throwing away its own thermal energy through this radiation. So, quick recap here. We need to make sure we're on firm footing with this terminology, and then we're going to hit an example and actually put some of this into practice. So, intensity. Okay, this is the flux per wavelength per unit solid angle in a specific direction. Okay, then by integrating across all visible space, we end up with the spectral power, which is the flux per wavelength in all directions. And then integrate across all wavelengths to arrive at the power, which is really, right, it's really a flux because it's really power per unit area. Flux in all directions across all wavelengths. Okay. So I just want you to understand this difference between intensity, spectral power, and power. Notice I haven't said emissive here because the same terminology applies to irradiation. So we'll see in a second. So if we're talking about emission, right, that active throwing away of radiation by the thermal energy in an object, we would have spectral emissive intensity and spectral emissive power, and then just emissive power. Okay. When we get into irradiation, it would be spectral irradiation intensity, spectral irradiation power, and irradiation power. So hopefully I have not just confused everybody into a total stupor. It's kind of dense stuff. But let's go ahead and try tackling a simple example to see, kind of make this stuff a little bit more intuitive. So we'll solve this example in two different ways. One, using the more mathematical approach here, and the second, using a more intuitive method. All right. So let's imagine we have a diffuse. Oh, I forgot one definition here. Before we do this example, there's this thing we need to diffuse emitter. Okay. This is a very easy one, and it's a very helpful one. A diffuse emitter is a surface for which the spectral intensity is not directionally dependent. Okay, so what I mean by that is, right, we have our spectral intensity, I, lambda E, which is ordinarily a function of the wavelength and our two spherical coordinate angles. Okay, this simply becomes I, lambda E, theta. So it has the same units, it functions the same way, it's still sort of like a concentration of radiated energy, but what it's saying is that it's going to be uniform in all directions. And when we have this thing that's called a diffuse emitter, we can go ahead and write E lambda, right, our spectral emissive power, which now is a function of lambda, is simply going to be, right, it's going to be that same integral, 0 to 2 pi, 0 to pi over 2 of I lambda E lambda cosine theta sine theta d theta d phi, and this will simply work out to be pi times I theta E lambda. So when you hear something as a diffuse emitter, this means that basically, like I said, that this integral here becomes very simple in terms of scaling up that pi. Easiest way to remember, understand what a diffuser is. Okay, in almost any case where you see something called a diffuser, the idea is the same. It's to remove the particular directional bias of something. Right? Photography, people use flash diffusers or diffuse lighting to create like a soft lighting effect that does not cast harsh shadows. Right? So when you see someone shining a light backwards into one of those foiled sort of umbrellas, that's precisely why they call it the diffusers. It's removing a bunch of that directionality from the light. Okay, so with that definition out of the way, now let's get to the example. So let's imagine we have a diffuse emitter with a surface area A1 is equal to 10 to the negative third meters squared. So we'll say here's A1, and there's also another surface, A2, that has the same 10 to the negative third meters squared, the same surface area, but is located, right, at an angle of, my eraser's not working anymore, of 30 degrees from the horizontal, from A1. So people have gone out with probes and they've measured the radiation intensity, okay, the spectral radiation intensity from A1, and what they figured out was they put a probe right here, and they figured out that IE which is, or sorry, not the spectral radiation intensity, what's known as the total radiation intensity, which is the radiation intensity across all wavelengths. So I lambda E d theta, right, is equal to 7,000 watts per meter squared steradian. So understand that we just did the integration across all wavelengths first. So this is the sum energy across the entire band of electromagnetism. So we could do a quick sketch here. This is also 30 degrees. If we have, right, say this is 60 degrees, and then let's say this is a little bit awkward, that the distance from this point to, let's call this, we'll just call this B, and we'll call this point right here C. That B to C has a length of 0.5 meters. Okay. So what's going on here is, right, A is our emitter, and A2, or A1 is our emitter, and A2 is going to be some surface that is intercepting some of this this emitted radiation. So what we're going to try to find is three things. The intensity of radiation in the direction of A2, the solid angle subtended by A2 at the center of A1, and the irradiation, or, intercepted radiation from A1 to A2. Okay. So three things. Our only assumption that we're going to operate on here is that A1 and A2, right, are very small, which is kind of implied by the fact that these are, right, 10 to the negative third meters squared. So with these three things kind of in our heads, these are what we're looking for. We should be able to answer A right off the bat, just by inspection. Okay, anyone want to hazard a guess? So, radiation intensity. Okay, think about the definitions before. This reflects the dependence on wavelength, if we have that, and on direction. Right? We've said that this is a diffuse emitter where the direction dependence goes away, and so it's constant in all directions. And we've given the radiation intensity at one point in space. Right? So those three things together should tell us that the radiation at any other point in space, in any other direction, is going to be the same as that measured for that little red dot. In other words, the radiation coming off from a point on A1, okay, is going to be 7,000 watts per meter squared steradian, regardless of where it's being measured. Okay. So, in the direction of our surface A2, it's also going to be, i.e., is also 7,000 watts per meter squared steradian in all directions, including that of A2. Right. For part B, okay, what is the solid angle that is subtended by A2 at point B, right, on A1? For this, we're going to draw another little sketch. Let's say this is A2. Okay. Here's our point B, which is on A1, of course. So what we're interested in is figuring out the solid angle represented by this projected kind of cone or pyramid or whatever cross section it has. Okay, we don't know anything about the shape of A2. It could be a flat plate square, it could be star shaped, it could be some random organic shape. The question is what's going to be omega. So the way we figure this out is we're going to draw the projected area of A2, right? So here's A2's sort of silhouette as seen from point B. We're going to draw the ray connecting B to this silhouette, which should form a right angle. We know that that ray there has radius of 0.5 meters because that's what was defined sort of in the initial sketch here, right? From points B to C here is a distance of 0.5 meters. So just like in the case before, right, the projected area is going to involve some cosine. So this angle we'll call theta 1. This angle we'll call theta 2. The question is which one of these is going to affect sort of the apparent area of this silhouette here. Or rather, which one's going to affect it as a cosine. We can figure it out from either one. But if we say that, we could say that AN, which is the, right, the eraser, the silhouette area is equal to A2 cosine of theta. The question is which theta we should use for that. And I heard somebody say A2, which is the correct answer in this case. All right. It's going to be the angle, right? It should be the angle, the difference in angle between the normal of the surface and the direction from which it is being viewed. Okay, so we need to shift our focus over here and just sort of say we know that this is the ray from which it's being viewed. The surface normal to this angle should be, or the surface normal to A2 here is going to be this horizontal line, and so the difference between those is theta 2. And so we'll go ahead and use this as our projected area, right? So that's the area that is occupied in terms of the visible space from B. That's the area that is actually sitting in the visible range from B. And so to find the solid angle, we've got our definition from before, right, where solid angle is equal to area over r squared, which in this case is going to be A2 cosine theta 2 over 0.5 meters squared. All right. So we figured out the subtended angle. So if we plug everything in, right, that's going to be 10 to the negative third meters squared cosine of 30 degrees over 0.025 meters squared. And this will work out to a value of 0.00346 steradians. Very exciting. All right. Now, knowing the solid angle, the rest of it should, our last part, right, part C of this problem, should be pretty easy, figuring out how much irradiation from A, or how much radiation from A is actually being intercepted by A2. So for part C, right, we've got, we'll draw this sketch one more time. Promise I'll cut it out with the drawings here in a second. So the idea is, right, we can write from before, we'll rewrite what we had before, that D, right, the outgoing radiation in a particular direction and across a unit or a unit solid angle can be written as, let me go ahead and pull this back up. Go. I mean I theta E, or in this case we'll just say I E times the small unit angle through which it's going times D times cosine of theta, where theta is now the direction in which that radiation is going. And so what this represents is the amount of energy flux out of this object going in this direction across this small region, this small solid angle. Okay? And so what this is telling us is basically, here's how much energy per unit area at a single point on the emitter is being cast toward A2. So we could say dq from 1 to 2 is our IE times cosine theta times our 3.46 times 10 to the negative third steradians. And so the way we need to, what we need to do then to figure out how much total energy is simply to integrate this over the surface area of the emitter. And so to figure out Q, 1 to 2, that's not a Q, that's a D. This would be integral over A1 of D Q double prime from 1 to 2 dA. And in this particular case, right, the point of that assumption, we're saying that A1 and A2 are very small. Basically, what that allows us to do is say that from this point to this point, the angles involved and the solid angles involved aren't really different, okay, that they're about the same. In other words, everything inside of the argument of this integral remains constant, and it can come outside, and so we end up saying that Q from 1 to 2 is going to be equal to, right, our IE cosine theta times our solid angle times A1. That theta, we'll go and plug in our 30 degrees so we don't get confused. Times cosine of 60 degrees. All right. And so plugging everything in, that would be our 7,000 watts per meter squared steradian times cosine of 30 degrees times cosine of 60 degrees times 3.46 times 10 to the negative third steradians times area 1, which is 10 to the negative third meters squared. And this should all work out to a value of 12.1 times 10 to the negative third watts. Fairly complicated process. Sorry, we went about 30 seconds over. We're going to leave it off here. In the next lecture, we'll pick up by showing a way that we get the same answer that's maybe a little bit more intuitive. This is an example that's in 11.3. It does it for 3 surfaces scattered around A1. So you can, if this is just got you completely lost, I recommend you take a look at that example in the book.